For years, the AI industry competed on a single metric, building bigger, smarter models to top benchmark charts. But as open-source models converge on the capabilities of closed-source frontier labs, raw intelligence is no longer the sole differentiator. The industry has moved into a second phase of development. The challenge now is delivering that intelligence instantly. Look at how user interactions evolved. A standard single-shot prompt requires a baseline of 1x compute. Modern reasoning models that plan, decompose, and verify require 100 times that compute. Moving to autonomous, multi-agent workflows multiplies that demand by over 1,000. Because every token generated requires physical compute power, this compounding latency creates a severe bottleneck. Building advanced AI applications today requires pushing models to run faster than ever before. The turning point happens at the 500 millisecond threshold. When a model reliably returns a response in under half a second, the interaction stops feeling like a background task. It behaves like a standard, instant function call. On the left, we see traditional slow inference, relying on UI tricks like spinning loaders and text creeping across the screen. On the right, a model streaming at ultra-high speeds executes complex personalization logic instantly, rendering a fully populated web dashboard in a single flash. Hitting these sub-second speeds from massive language models cannot be achieved by tweaking software or shrinking precision. It requires a physical re-engineering of the silicon itself. To build the next generation of instantaneous software, engineers need to look at the physical constraints limiting our current hardware, the data movement bottleneck. Traditionally, processors are made by cutting a large silicon wafer into dozens of smaller pieces, discarding any defective ones. This yields relatively small, individual chips, like standard GPUs. This schematic shows a standard GPU chip. Notice the small inner square. That is the onboard cache, which maxes out around 80 to 100 megabytes. It is separated by a narrow bridge from the much larger external high bandwidth memory, or HBM. Modern language models are massive, often requiring gigabytes of space. Because they cannot fit into the on-chip cache, their weights are stored entirely in that off-chip HBM. This creates the memory wall. To generate text, the system executes a physical weight commute. For every single tiny token produced, the model's entire multi-gigabyte parameter matrix must stream across that narrow bandwidth bridge to reach the compute cores. To compensate for this slow commute and keep the math units busy, traditional hardware providers group dozens of users together into batches. This maximizes overall system throughput, but increases the wait time for every individual user. The ceiling on standard LLM inference is not how fast the GPU calculates matrix multiplication. The limit is the physical distance the data must travel to get to the math. Wafer-scale engineering solves the memory wall by bypassing the dicing phase completely. The entire silicon wafer is kept intact. The Cerebras Wafer-Scale Engine 3 houses 900,000 AI-optimized compute cores on a single monolithic surface. This massive footprint allows the chip to hold 44 gigabytes of on-chip SRAM. This diagram illustrates how those massive weight blocks are loaded directly into specific regions on the wafer, locking firmly into place right next to the compute units. This reverses the entire execution pipeline. Instead of constantly moving gigabytes of weights to the math, the weights stay perfectly still. The tiny token data packet sneaks its way through the physical layers of the chip. The physical data commute shrinks to just 0.1 millimeters. This results in 21 petabytes per second of memory bandwidth, providing speeds exceeding 1,200 tokens per second, all without needing to batch users together. By eliminating the physical data commute, the hardware removes the latency ceiling. For developers, this changes how software can be structured at the most basic level. Generating thousands of tokens per second allows software engineers to delete layers of complex handling machinery. This flowchart illustrates the traditional slow path. Because GPU latency forces a multi-second wait, applications require an asynchronous architecture. A client request triggers a queue, a background polling loop checks for updates, and mutable job states are tracked before finally returning a result. This places a heavy burden on the developer, who must build and maintain background worker threads, orchestrate retries, and design UI loading states just to keep the user engaged. Wafer-scale inference makes a fast cap possible. The heavy orchestration machinery is removed. The architecture collapses into a direct, straight line from client request to immediate result. Complex multi-step workflows, like categorizing an issue, searching a database, drafting a reply, and writing an internal ticket, now execute sequentially in a matter of seconds. Extreme inference speed lets developers revert to straightforward, synchronous code, keeping the user in an unbroken state of flow. We can see this synchronous architecture in action by building a real-time agent that ingests and evaluates live market signals as they hit the wire. Building a system this fast requires strict constraints. We use pygantic schemas to force the language model to return highly predictable JSON objects, eliminating parsing errors when mapping data to our workflow. This decision tree shows a dynamic router. When an incoming market signal arrives, a fast classification model analyzes it instantly, routing the data down one of 4 distinct paths: ignore, quick update, fact refresh, or full review. The agent strictly follows the lightest useful path. If a signal reinforces a prior decision, the workflow drops straight down to a quick update, completely skipping the heavy database and comparison tools. Because the core inference takes mere milliseconds, this entire process of evaluation, routing, and tool execution finishes before a user even perceives a delay. Fast inference allows you to run classification models before triggering heavy actions, ensuring your autonomous agents only spend compute cycles where they actually matter. Moving to a 1200 token per second workflow introduces a critical new engineering hazard: rapid context compaction. This chart plots context usage against model precision. A fast model can burn its entire context window in under 30 seconds. Precision holds steady in the green zone, but plummets sharply into hallucination and instruction drift, a degradation that takes 10 minutes on slow GPUs. To avoid this trap, developers adopt an orchestration pattern. You divide the labor, using a massive, slow model to map out a structural plan and an ultra-fast model to execute narrow, specific steps. State is managed strictly outside the model's memory using a 4-file system: one for agent rules, one for the checklist plan, one for a progress log, and one for strict verification commands. The fast execution agent is continuously spun up, fed the state files to complete exactly one checklist item, and immediately torn down. This ensures it always starts with fresh, empty context. Because inference happens in fractions of a second, the time cost of running these constant validation loops and pre-commit checks drops to virtually zero. At wafer-scale speeds, the developer's role shifts. You spend less time writing code alongside an AI and more time orchestrating aggressive, state-managed execution loops. Keeping the massive silicon wafer completely whole solves the core data movement bottleneck. That bandwidth eliminates the latency ceiling, which directly enables synchronous request-response application architecture. In computing history, intelligent systems always arrive first, but it is the advent of fast hardware that makes entirely new categories of applications practical. This transition to wafer-scale inference means language models are evolving. They are moving from passive tools that slowly respond to prompts into real-time engines capable of driving live, autonomous software. By escaping the memory wall, developers are no longer fighting wait times. They are free to design software that is both instantaneous and deeply collaborative.